All right. Hi, good afternoon. How are you guys doing? Okay, so first of all, let me welcome you guys to the Unacademy JEE English. This is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And here on this channel, everything is being taught to you completely in English. So this is a series which is meant for 2021 aspirants. All right, so students who are currently in their class 12 and they're looking to take their JEE examination next year. And so what we are doing is we are taking every topic one by one. We are discussing the fundamentals and we are discussing the problem solving strategies. So today is lecture 5 of this series and we are discussing capacitors today. Okay. So the subtopic for the day is of course dielectrics. All right. So before we get started, let me introduce myself one more time for those of you who don't know me. My name is Rohit Dixit. I studied mechanical engineering from IIT Delhi, and for the past almost 8 years, I've been teaching physics for IIT JEE. And all my teaching experience so far had been in the offline setups, but I have been associated with some of the topmost institutes in the JEE field. Now, I myself was JEE rank 447, and I've coached many students to top ranks in IIT JEE. And I hope to continue doing that here or with this Unacademy's online platform with all you guys. So before moving forward, let's also talk about the Unacademy subscription and its benefits. So your Unacademy subscription comes with benefits like live classes, you get to interact with your educators. So these two are very useful features. I mean, they are trying to bridge the gap between the offline and the online coachings. All right. Plus, you have live polls and leaderboards. Hi, Manish Pandey. How are you? So these make your classrooms extremely interactive, which is very nice. And then you have test series and analysis so that you are constantly evaluating your performance and constantly improving it. And best of all, you have live doubt clearing sessions. So I know these days students are really panicked about where to go for their doubts, who to consult because everybody is locked down in their own places. So with Unacademy, you won't have to worry about your doubts again. Because as a compulsory feature, all the courses on Unacademy Plus have a doubt clearing session after every 3 sessions. So if you're really worried about all this, don't worry, get your Unacademy subscription and everything would be sorted. Alright, on top of all these benefits, you also get access to India's top educators with your Unacademy subscription. So Unacademy has brought the best educators in India on this single platform so that students are not. Alright, hi Ramesh, how are you? So that students have no confusion as to where to go to study, who to study from. Alright. Next, so how do you get the subscription? Very easy. First, you install the app. Once you have installed this app, then you go to the IIT JEE. You select the plus segment. You select your goal as IIT JEE, and you click on that Get Subscription button. All right. Now, if you look at the pricing of these subscriptions, these pricings have been kept very affordable, very fair. I think the 12-month subscription comes at about a cost of 2,500 a month, and a 24-month subscription comes at about 1,500 a month. All right, so these fees are much lower than what people pay for their class 5, 6, or even smaller classes. All right, and this is obviously absolutely nothing compared to students pay in their offline setups because I have been a part of offline industry. All right, so I know what kind of fees students are paying there. Now, this already very affordable subscription can become even more affordable if you use my code RDLive to get your subscription. So remember to use my code RDLive and you will get an additional 10% off on your subscription fee. All right. Next, moving forward, for those of you, all right, who are following us on the JEE English channel can also connect with us on the on the Telegram app using the link shown above. All right. There is some lag. You are right, Mr. Manish. Okay, let me see. Yeah, the net is fluctuating a bit. You are absolutely right. So okay, let me try and reconnect this. The net is fluctuating very highly. Okay, let's see if it smoothens now. It seems much better now, steady now. Yeah, I just checked my settings. Thank you for letting me know, Manish. All right, so yes, Manish was saying price can be reduced or not. Free subscription. Okay. So Manish, we are already providing classes on this Unacademy JEE English channel for free. All right. So if you want proper courses, if you want to enroll in regular courses on the app, then you can get the subscription. If you can always follow us on the JEE English channel. Content here is absolutely free. Okay. Yes, I know, I know. My net is fluctuating a bit. Okay, so let me see what seems to be wrong here. All right. In any case, pricing is already very, very affordable. You realize I told you that the 2 year subscription is coming at a cost of 1500 rupees a month. I'm sure you know people who pay much more than that for their school tuitions. All right. Okay, the lag is back. So please suggest any educators in the Unacademy who teach only in English. So Sabrish, as of now, from what I am aware of what I think it's only the JEE English team that is taking lectures in English. Rest everybody has been taking lectures in Hindi only. Okay. Hi Siddharth, how are you? All right. So as I was saying, today is lecture 5 of our series of capacitors, and today we'll be talking about dielectrics. All right. So what exactly are dielectrics? Let's get started with the topic. Yes, my net is fluctuating a bit, so you'll have to bear with it. I hope it will get steady because it just fluctuates a little in the middle. I don't know why. Yes, Sabresh, I told you in Unacademy app also there will be courses. Okay, I think the JEE English team will be starting courses from September. Okay, so don't worry about it. You will be taken care of. All right. So, coming back to the topic of the day, what are dielectrics? A dielectric is a substance which is essentially an electrical insulator. So, dielectrics is another name that we use for insulators. All right. And these insulators have a property that they can be polarized in an external electric field. All right. Now, dielectrics are categorized into two ways. So, one are called polar dielectrics and another is non-polar. We'll talk about what polar and non-polar is. So, first of all, you need to understand the basic. That dielectrics is nothing but another name given to insulators. So, in our previous classes, we already studied about properties of conductors, and now today we're going to talk about the properties of dielectrics or insulators. Yes, Sabresh, as I said, we will be starting the JEE English team would be starting lectures on the app in September. All right. So don't worry, don't worry. It will be taken care of. Next, coming back to dielectrics. A dielectric, what that does is that it weakens the field inside it because the molecules of a dielectric produce an electric field within the dielectric, which has a direction opposite to that of the external field. So see, this is something which is happening. All right. Hi Siddharth, how are you? So when you put a dielectric in an electric field as shown, you will see that these charges will start appearing on the surface. We will talk about this in detail, and another kind of charge will start appearing here. So these charges will end up creating their own fields, and their own fields, as you can see, would be opposite to that of the electric field. This will result in weakening of electric fields inside the dielectric. All right. We have turns out great use for that, and that is why we are studying dielectrics, and that is why we use dielectrics. All right. So let's move forward. All right. Okay, so moving forward, as I told you that dielectrics are of two types. One is polar and another is non-polar. So what are these? Let's talk about that. So polar dielectrics are those which have a net dipole moment on a molecular level. All right, you know in nature the molecules that exist, they have a dipole moment, electrical dipole moment. I'm talking about electrical dipole moment here. For instance, you take a molecule of H2O. So it is something like this. So because of the high electron affinity of the oxygen, there is a delta negative charge that appears here and slight delta positive charges that start appearing here. So obviously this is a sum of two dipoles with dipole moments like this. So vector sum would be somewhere here. So this water molecule has an inherent dipole moment. All right. All right. So that is a dielectric. It is a non-conductor, but it has a dipole moment on a molecular level. Similarly, there are non-polar dielectrics. So what are these dielectrics? These dielectrics have no net dipole moment on of their own on molecular level. So imagine one of the examples is air. So air is mostly N2, right? Nitrogen. So nitrogen, this N2 does not have any dipole moment. All right. So this is an example of a non-polar dielectric. So polar dielectrics would be anything which has a dipole moment on a molecular level. Similarly, non-polar dielectrics are those who do not possess a dipole moment on a molecular level. I hope everybody remembers what dipole and dipole moment was. We have discussed this earlier. Alright, so if you don't know, please go over that lecture. Alright, good afternoon, Vineet. Alright, so moving forward. I hope you guys are all following this, that there are two kinds of dielectrics, polar and non-polar. Okay, let me know if you're following this, then we will take the discussion forward. Okay. Now there is something which is called polarization. Now polarization and polarization vector. So polarization is a process and polarization vector is a mathematical quantity which is used to measure the amount of polarization. So first of all, let's talk about the mathematical quantity polarization vector. So polarization vector is defined as the net dipole moment per unit volume. Alright. So what you have is, you may have a lot of dielectric which is made up of a lot of dipoles, right? So maybe you have different dipoles inside this. Some here, some here, some here. So these are different dipoles, imagine. Alright, I'm talking about electrical dipoles, by the way. So when you take up a small volume, imagine you are considering a small volume. So if in this small volume, the net dipole moment is some P, and this has a volume V, and net dipole moment is P. Alright, which is the summation of all the dipoles which lie in this volume. Alright, so polarization vector capital P is represented as summation of all the dipole moments which lie inside the volume V over volume V. Alright. Okay, so what is going on? Vineet and Siddharth in YouTube, which channels do you guys see for physics other than Unacademy? Okay. Guys, it would be better if you can focus on the lecture right now. Okay. Anyhow, so that is how you define polarization vector. And what is polarization? Whenever a dipole, a dielectric gains a net dipole moment per unit volume, we call it to be polarized. Okay. Alright, now in absence of an electric field, the net dipole moment per unit volume is 0 for all dielectrics. So what is happening is, imagine a dielectric which is kept in air and there is no external electric field present. Now what happens? Alright. Okay, Vineet, thank you, and please focus on the lecture, because this is something which, trust me, is not discussed in books also in great details. Okay. So I would advise all you guys to pay a little more attention here. Okay. This polarization and dielectrics is not discussed in too many details in any of the books. So if you want to understand what dielectrics are, why they behave the way they do, so please pay attention. All right. So as I was saying, yes, thank you, Vineet. Alright, as I was saying, in absence of an external electric field, the net dipole moment per unit volume is 0 for all dielectrics. So I said, what are the kind of dielectrics? Dielectrics can be either polar or non-polar. Now I'm saying that in absence of any external electric field, both of them will have a net dipole moment per unit volume 0, which means polarization vector for both would be 0. Why so? Let's see. Now, in case of non-polar, it is very easy to see, because non-polar molecules in any case do not have any dipole moment. So imagine a sample of, let's say, nitrogen. So it has nitrogen molecules. No molecules have a dipole moment in any case. So if they on a molecular level if they don't have a dipole moment. So obviously the dipole moment per unit volume would also be zero, and I can say that P vector for this would be zero. How about a polar molecule, however? Polar molecule already has a dipole moment on the molecular level. However, when you look at a dielectric, the point is that all these dipoles are randomly oriented. Alright. So all the dipoles are randomly oriented here. And you know that polarization is a vector. It is the sum of dipole moments. Alright. Since all the dipole moments are equal and they are randomly oriented, so sum of their dipole moments comes out to be zero. Alright. So this is zero. That is why capital P is also zero. Alright. Because summation of small p is zero. So I hope you followed the logic that for both polar and non-polar dielectrics, the value of polarization vector is always zero in absence of external electric fields. Alright, please let me know if you're following this. And as I said, this is something which is not discussed in a lot of books. Alright, so you will need to follow me to understand this proper. Alright, are you guys following this? Should I move ahead or do you want me to explain something again? Let me know. Alright, let me know quick, guys. Okay. Alright. So since nobody seems to be objecting to anything, so I'll just move forward. Now, what happens when you keep a dielectric in an external electric field? Now, what happens is that any kind of dielectric gains a net dipole moment per unit volume and hence has a non-zero polarization vector, and now we say that the dielectric has gotten polarized. Alright. So please note that when a dielectric is placed in an external electric field, it gains a net dipole moment per unit volume. How is that happening? Alright, so imagine this. So how is that happening? Let's say for non-polar dielectrics. Now imagine a sample of some non-polar dielectric. Let's say it has XX molecules which are completely non-polar, which will be obviously completely non-polar because an XX bond, the electrons are not attracted to any side. Alright, so that is why the net dipole moment of such a thing would always be zero. So a lot of XX molecules are there. It could be N2, H2 or anything like that. Those can be examples of non-polar dielectrics. So now what happens is when I place this in an external electric field. Now what this electric field does is that it starts pulling the electrons towards one side. Alright. Now you notice that in this bond, what happens is that the electron clouds shift to one direction. Alright. And hence every molecule which did not have a dipole moment earlier now starts to gain a net dipole moment. Now you realize for this guy, alright, so let's mark this guy. For this guy, that will not happen. Why? Because all the electron clouds, what is happening in a bond? So if you have an XX bond, basically there is an electron cloud which some electrons are revolving around both the nuclei. This is the molecular orbital. I hope you guys have studied that in physics, MOTR, molecular orbital theory. Alright, so this is what is happening. The electrons of these bonds are essentially revolving around in molecular orbitals, and they are revolving around both the nuclei. Now what happens is if the electric field is like this, then this electron cloud shifts in the direction opposite to that of the electric field, and you will see that it becomes something like this. It shifts and becomes something like this. Now the moment the electron cloud shifts that way, now what appears to be happening is that this end of the molecule gains a slight negative charge and this end of the molecule gains a slight positive charge. So now they start behaving like a dipole. Alright. So in the absence of external electric field, the electron cloud was perfectly symmetric for both the nuclei. Alright. It was covering both of them uniformly. In the presence of electric field, this cloud gets shifted and hence one nucleus or one atom seems to have a net negative charge and another atom seems to have a net positive charge. Hence, even this non-polar molecule has gained a net dipole moment. Again, on this kind of an atom, it does not matter. On this kind of a molecule, even if the electron cloud shifts the other way slightly, the dipole moment would be negligible almost. All right, though it would appear that there is a slight negative here, slight positive here, but then that is almost contributing to zero dipole moment compared to these guys. So all these guys will start behaving as dipoles with negative charges here, positive charges here, negative charges here, positive charges here. So now when you measure the net dipole moment per unit volume, you will find a non-zero quantity. That is why your polar dielectrics or non-polar dielectrics are getting polarized. So here is the explanation in words also. So for polar dielectrics, what is happening is that they are acquiring a net dipole moment at the molecular level, and that is why now you can see a net polarization vector in them, or a net dipole moment per unit volume. Similarly, in polar molecules, what is happening is, I hope you remember the lecture about dipole in an electric field. When you place the dipole in an electric field, what happens? What happens? If I placed a dipole in an electric field, so here was my dipole. If I place it in an electric field like this, it feels a torque, right? And due to this torque, it will turn. It will turn and it will align itself. It will align itself in the direction of the external field. All right, because of this torque, it will turn and become like this. So that is what is happening here again. All right. Now you see one more thing. If you see here, the net dipole moment would be in the direction of external electric field for non-polar dielectrics. All right. Yes. So in non-polar dielectrics, you will realize that it gains whenever external field is applied. The dielectric is gaining a net dipole moment which has a direction in the direction of the external electric field. Similarly, for a polar, what is happening is that all the dipoles are turning in the direction of the external electric field. So now imagine, earlier what you had was, earlier you had a lot of small dipoles in a polar material. Alright, so this was already having a lot of dipoles. So one dipole here, one dipole like this, one dipole like this. All these dipoles were randomly oriented earlier. Now, as soon as I switch on this electric field, now what this does is it starts turning all the dipoles in the direction of the external electric field. So sometime later what you will notice is that this guy becomes like this guy is already like this guy becomes like this guy becomes like this may be left like this only. However, you see majority of the electrons have turned in the direction of the external, majority of the dipoles have turned in the direction of the external electric field, and this guy now also has a net dipole moment in the direction of the external electric field. So whenever you are putting your dielectrics in external electric fields, be it polar, be it non-polar, both of them will acquire a net dipole moment per unit volume, and this dipole moment would be in the direction of the external electric field. So remember guys, this is very, very important. This is what you call polarization of a dielectric. Alright. So once it has a capital P vector which is non-zero, now you say that the dielectric has got polarized. Alright. So this is what it is. So in presence of external electric fields, every dipole, every dielectric, no matter how that was, it will get polarized. Now, this polarization of a dielectric will result in some induced charges that will start appearing on the surface of a dielectric. Now, what do I mean by that? So let's see. Let's try and draw that again. Okay, so let's imagine that this was your dielectric. All right, and it was kept in an external electric field like this. And now focus that all the dipoles are turning like this. So you will have several small dipoles. You will have several small dipoles. So I'm making these dipoles like this. So it has negative here, positive here. So this has negative here, positive here. Negative, positive, negative, positive, positive, negative, and so on. All these dipoles, you see, all their dipole moments are pointing in the direction of the external electric field. Now imagine what is happening. Inside, if you look carefully, okay, so let's draw one more so that you can visualize this properly. Now, because all these dipoles are aligning themselves like this, what you will see is that on this surface, okay, so what you see is that on this surface, you will realize a positive charge starts to appear. Why? Because all the positive ends of the dipoles are there on this surface. Similarly, on the other side, what is happening? Imagine. On the other side, all the negative ends of the dipoles are appearing. That is why you will see a negative charge getting induced on the opposite surface. How about the middle? In the middle, if the dielectric is isotropic, we call these dipoles isotropic if the polarization is uniform throughout. Okay, so if it is a uniform isotropic dielectric, then inside you will see that there is positive here, negative here, positive here, negative here. So inside you don't see any charges. So and in JEE syllabus you only talk about isotropic uniform dielectrics. So in the dielectrics that we are going to talk about, when they are kept in external electric fields, you will see negative and positive charges getting induced on the boundaries and no net charge appearing inside the volume of the dielectric. Alright. Now, one more thing, that this charge that is induced it appears to be similar to the charge that appears in conductors. You remember that. If a conductor was placed, what would have happened if a conductor was placed in an electric field? You guys know that on this end it would have gained a negative charge, and on this end it would have gained a positive charge. Alright, this is how the charges would have gotten induced. So the charge induction is pretty similar. On the same side you're getting negative, on the same side you're getting positive. However, there is a slight difference. The difference is that here these charges were appearing due to movement of free electrons. And here the charges are appearing but they are still parts of dipoles. So these are not free to move. Okay, these are called bound charges. So please remember that all these, they are called bound charges. So these as well as these are called bound charges. So let's write that down. So both of these guys are called bound charges. The reason why we are calling them bound charges is that though they are appearing on the surface, they cannot freely move around, unlike the charges that would appear in conductors. Okay, so these are bound charges. Now, the polarization of a dielectric, we have already discussed this, results in induced charges appearing on the surface of dielectrics, again called bound charges. Now please notice what used to happen in case of conductors. In case of conductors also, these guys would have created their own electric fields, which would have been opposite to that of the external electric field, right? Because there would be a field which would go from plus to minus. So these induced charges used to start creating their own electric fields. And in case of conductors, this field would keep on growing because the charges would keep on increasing as long as there is a net field. Here that does not happen. Here once the dipoles are aligned, what happens is that this charge that is appearing, this starts creating a field which is opposite to the field applied externally. Now, however, once the polarization is complete, this field does not change. Alright, once the dipoles are aligned, once the dipoles have gained dipole moments, now there is a fixed amount of field that these guys are generating, and even if there is a net field inside, it does not matter. Why? Because this does not have free charges. Alright, all the charges are still bound to their molecules. Alright, so even if they have aligned themselves a certain way, even if there is a net electric field, you realize, even in a net electric field, all that happens to a dipole is that it aligns itself with the electric field. So if you had a dipole here, all that would happen to the dipole is that it will become like this. And that is it, nothing beyond that. Alright, so similarly, in these kind of materials, in dielectrics, that is, once the dipoles have aligned, now even if there is a net electric field inside, it does not matter, that cannot change anything. Alright, however, this polarization will create its own electric field. Alright, these induced charges due to polarization would create their own electric field. The direction of this electric field would be opposite to the external electric field, and this is what leads to the electric field getting reduced inside a dielectric. Alright, so let's go over this. So these charges, called bound charges, create their own electric fields in the direction opposite to that of the external E, thereby reducing the net E inside dielectrics. Alright, now let's talk about mathematics of polarization. Alright, so okay, again you guys will have to pay close attention to this, because the maths that I'm going to show you is not usually easily shown in books, and there is some bit that is shown in NCERT, and there they have written a wrong equation. So please pay attention to this. Okay, so what happens is that you guys know that the net electric field that would be inside would be E net vector would be E due to external minus E due to bound charges. Alright, this would be the net external electric field. Now, one more thing, it was experimentally noticed for small E net. Okay, so for small values of E net, as long as your net electric field inside the dielectric is small, turns out the polarization vector is directly proportional to the E net. Alright, so please remember this, that this is an experimental result. Experimentally it was found that E net is directly proportional to the polarization vector, or you can say the higher the E net, the higher would have been the degree of polarization. Okay, why is this happening? Again, imagine if consider there was a non-polar molecule, alright, X kind of molecule. If I increase the external field, the shifting of the electron clouds would be more and more, alright, which would result in more polarization. Alright, and obviously if external field is more, then you will realize E net is also higher. So if you're increasing your external field, the polarization is higher, and the higher external electric field also leads to a net higher electric field inside. Okay. However, what happens if I keep on increasing that electric field? See, the distortion of this electron cloud initially would be linear, then it won't grow in that proportion. Okay, so initially imagine if the electron cloud is shifting a bit, if I double the electric field, it maybe shifts double, but beyond a point it won't be able to shift too much, alright, because it cannot leave this end. So that is why this relationship is only linear for small amounts of E. Similarly, you realize that the turning torque of the electric field for a dipole is P cross E. So higher the value of E, higher would be the turning torque, and that is why as you keep increasing your external electric fields, more and more dipoles will start turning in the direction of the external electric field, which will cause a higher polarization vector. However, this again initially would be linear relation, alright. If certain E causes X number of dipoles to have turned, turns out 2 times that E would call 2 times the number of dipoles to turn. But if you keep on increasing that, you realize beyond a point when all the dipoles have turned, you won't see an increase in polarization vector even if you go on increasing your E external. Now, if you go on increasing your E external, E net would also increase. Why? Because this cannot increase. Because the appearance of bound charges is complete. All the dipoles have got aligned. Alright, I don't know if you guys are following this, but I hope you are. In any case, since there are very few people who are watching it right here, so if you have any doubt regarding the discussion that I'm trying to have, you can always write in the chat and I will try and explain. So till the time, let's talk about this. What happened? What happens is that E net is being reduced by the E due to the bound charges, as we saw here. Alright, so bound charges creating their own E. This is what I'm calling E bound. Alright, so let me write it in orange only. So this is what E bound is. You can see the direction of E bound is opposite to that of the external E. And this is my E external. Okay, this is my E external. So what would be the net E inside? It would be E external minus E bound. Okay, this is what I've written first. Now experimentally we have realized that for small values of E net, the polarization vector is directly proportional to E net. Now what we do is we remove the proportionality sign and we introduce a constant of proportionality. So now next we write this as xe times epsilon naught times E net. Alright, the reason why I am adding an epsilon naught also is to maintain the dimensional homogeneity. Alright, why? Because xe is considered to be a dimensionless constant. Alright, so xe here is a dimensionless constant. So let's talk about this. What is this? So this is a dimensionless constant which is called electrical susceptibility. Alright, so dimensionless constant. Constant called electric susceptibility. Alright, what is electric susceptibility? I mean, you can imagine, consider two dielectrics. Consider two dielectrics kept in the same external electric field. The dielectric which has more susceptibility will have more polarization vector. So what susceptibility is means is that how easily it is getting polarized, how susceptible it is to get polarized. That is what electric susceptibility means. Alright, how easily your dielectric gets polarized. Okay, so I hope you guys are following this so far. This is the equation that we have got right now. Now we will claim one more thing. I will claim that for the sake of simplicity, I am taking a dielectric which is like this. Alright, and inside all the dipoles are getting aligned like this. Alright, so what do you see on the boundaries? I am only drawing the charges on boundaries. So on the boundaries you are seeing negative charges appearing here and you are seeing positive charges appearing here. Alright. Now, if the charge densities of these charges that are appearing on the boundaries is sigma b. So sigma b is the charge density. Okay, so let's use some other color. Alright, how about this? No, this would be too bright. Maybe this. So here the charge density is called sigma b. Sigma b meaning this is the charge density of bound charges. Alright, Sandmaster, please, next lecture start magnetism. No, Sandmaster, the next lecture would have to be electricity, current electricity. Okay, but that makes drawing for me easier. Okay, so I will leave it zoomed out. Don't worry later. But it makes drawing for me easier. That is why I keep doing that. Okay, Sandmaster, I will try to minimize it. So next what you can follow is that if you talk about a volume, small volume like this, all right, let's consider a small volume of the dielectric like this. Okay, now what is happening is that there is a charge which is here. All right, so let us assume there is a charge dq here. I'm assuming a very small cross sectional area dA. All right, there is a very small cross sectional area dA, and this area has a small charge dq. Yes, Sandmaster, but both me and Murli sir are supposed to take our own individual series. All right, I know, but again, both of us are supposed to take our individual series. All right, now you will see. I am also taking capacitors. He's also taking capacitors. All right, so it's not like some topics I am supposed to cover, some topics he's supposed to cover. I will cover all the topics in my series. He will cover all the topics in his series. Okay, you can watch any one of them. Okay. Now imagine if this length was L. If this length was L. Now what can I say? What is the polarization vector? The polarization vector is nothing but the net dipole moment per unit volume. Alright. Now please note that when the net charges are appearing, I see a negative charge here, I see a positive charge here. In the middle, I'm not seeing any charge. So I can treat this entire unit to be a dipole where one end has a negative charge, this end has a negative charge, and the other end has a positive charge. Alright, this is what I see. I see a dipole with positive charge at one end, negative charge at another end. So what will be the polarization vector, which is the polarization vector, which is the dipole moment per unit volume. So the dipole moment of this dipole would be dq times L. Alright, so per unit volume, it would be dq times L over the volume, which is dA times L. So let's start writing that. Alright. So let us start writing that. Now I can say that polarization vector can be written as the net dipole moment per unit volume, and net dipole moment can be written as dq times L over dA times L. So what you realize is, again, I'm talking about the mod here. Alright, so what you realize is this is dq over dA. I use this lecture to study entire class 12th. Yes, you can. Yes, you can. No worries. Magnetism, Sabrish, would be after we complete current electricity. Alright, so current electricity will not take too long also, because I have already discussed a lot of circuit solving in capacitors. Alright, so let's say give like 2 weeks for current electricity. So after 2 weeks we'll start with magnetism. Alright. So dq by dA, you will realize, is nothing but sigma of bound charges. So this is another important relationship. This is important. Alright, please remember that the magnitude of P vector would be equal to sigma of bound charges. Alright. Okay. So this is another important relationship when it comes to dielectrics. Next, I will now use this relation. So we have 3 equations right now. Now we will start substituting everything in these 3 equations. Alright. So now I can say E net from here I can say that E net can be written as P over XE over epsilon 0. Alright. This would be equal to, okay, I don't need to do that. Okay, not really. Yep. Wait. Let me show you it some other way. How about the bound electric field? What can you say about the bound electric field? You remember, just like conductors, all right, if you remember this, in conductors, if this guy had a plus charge, this guy had a minus charge in your capacitor, what was the electric field between them? This electric field, E, would be equal to sigma over epsilon naught. Alright. Now the charge distribution is very, very similar here. So E due to bound charges, E due to these charges, which would be in this direction, can be written as E bound would be equal to sigma bound over epsilon naught. Alright, I hope you can see. It is very similar. Okay, it is very, very similar to how you calculate E in conductors. See, the charge distributions are exactly the same. You have two parallel plates which are having sigma each. So the net E due to bound charges would be sigma B over epsilon 0. Now that is what I will write. I will write, since I got P vector equals sigma epsilon naught. So from here I can say that E bound would be equal to sigma bound over epsilon 0, which is nothing but P over epsilon 0. Alright. And from this relationship, what I can write is, again, please notice that here I am only talking about the magnitudes. The directions will be taken care of because I am writing plus here. Okay, so this should be plus here. To take care of the directions, I will turn this plus into minus. Okay. So please remember this. Alright, next I can say that E bound is equal to, from the value of P, I will substitute from here. So it would be XC times epsilon naught times E net over epsilon naught. So this is XC times E net. Now what I do is I substitute this value in this equation. So this is equation number 1, this is equation number 2, this is my equation number 3. Alright, now substitute this in 1. Put this in equation 1. So when you put this in equation number 1, what do you see? You will see that E net equals E net. Now I am removing the vector signs, so that is why I will introduce a minus here. Equals E external minus XE times E net. So from here I have a very, very interesting result. The result that I have is that E net equals E external over 1 plus XC. Alright, now please remember that this is a very, very useful result. Alright, so I had already told you that inside a dielectric, the electric field gets reduced. And now we have a mathematical relationship to how much it will get reduced. If you have kept a dielectric in an external field, which is E external, then inside the dielectric, the field reduces by a factor of 1 plus Xc. Now this 1 plus Xc is what you call dielectric constant. Hi Yasir, how are you? Alright, so now you know what this is. This is what your dielectric constant is. So 1 plus Xc, this term. Okay, so let's use some other color maybe. Yeah. So this is called dielectric constant. All right. Yes, Yasir, I definitely do. And we use the symbol for this K. Alright, so K equals 1 plus Xc. Alright, now I wanted to tell you what we meant initially when I told you that, in Coulomb's law equations or in electric field equations, you use a term which was, permittivity. So what was that permittivity? So if you remember, If you remember earlier, we talked about that E of a point charge, or let's just write magnitudes. Okay, so let's forget about the vector sign. E was 1 over 4 pi epsilon q over r square. All right. So this is not epsilon naught, this is epsilon. Where epsilon was called the permittivity of the medium. Now think about it. Now think about it. If you have a charge, imagine if you have a charge. So here is your charge, and it is kept in a medium. It is kept in a dielectric medium. Okay, so let's imagine that this is kept in a dielectric medium, and dielectric medium has a dielectric constant K, or permittivity, which is epsilon. So let's write about permittivity only right now. So let's say this has a permittivity of epsilon. Then what should your E be? So I can say that E is equal to this. Alright. Now, without this dielectric, what would have been the E? So I can imagine that I applied an external field in this dielectric, and that would have been Q over 4 pi epsilon naught r square. Alright. And now, let's talk about the relationship that we studied here. Here we realize that E net is E external over 1 plus XC. So now if I compare those, what do I get? KQ over 4 pi epsilon r square would be equal to 1 over 1 plus XC times Q over 4 pi epsilon naught r square. So you realize all this would get cancelled. And that is what your susceptibility is, permittivity is. E becomes epsilon naught times 1 plus XE. Alright. This is what your permittivity is. So what is your permittivity? If you realize, permittivity is what fraction of the electric field any medium is allowing. So if something has infinite permittivity, so the electric field would be zero inside it. So it does not allow electric field to go through it. So you realize every medium, what they do is, every medium reduces the electric field passing through them. So it does not permit the entire field to pass through it. That is what we call permittivity. Permittivity of any medium is epsilon naught times 1 plus Xc, and this term is also called dielectric constant K. Alright, so please remember these terms, and this was electric susceptibility. Alright, Yasser is saying something, so please guide me. What should I do? PCMB or PCM? So, Yasser, what do you really want? What do you really want? What do you really want? What do you want to do? Tell me. What is it that you want to do? Just think about what you are really passionate about, what you really want to do. See, because both medical NEET exam and JEE exam are highly competitive exams. Alright, and you will need to put in a lot of hard work in for both of them. If you want to crack any of them, you will have to put in a lot of hard work. So you decide which field you can feel motivated more. Okay, so if PCM it is, then PCM it is. What's the but for? You don't need a but. That's all right. That's all right. That is what you can do. You can study online now. I know the conditions in Kashmir are not really good. Okay, but yeah, so your net might also be a problem, right? Is that what you're trying to say? Let me know how I can help. See, whether it is PCM or PCMB, you have to study for both, right? And it's just Personally, I feel it's just better if you focus on one of these competitions. Hi Himanshu, how are you? All right. So try and focus only on one, and as you already said that you are more passionate about PCM, so go for PCM. Don't think about it. You will figure out a way. Okay. Okay. So try and get some decent internet connection. Maybe see cell phone internet services are hampered, but maybe your broadband services would be fine. All right. So I don't know. I don't know how it is. Try and get a working broadband net. Okay, and then you can study from the comfort of your home. Okay, Yasir. And it is unfortunate that you guys are having such a tough time. But then I sometime it came to my mind for PCMB. No, that would be unnecessary pressure. That would be unnecessary pressure. That would be too much of work. See, people already struggle about their IIT JEE prep. They start in class ninth. This is the new trend. A lot of even a lot of top 100 rankers that I have taught in the past few years are those who have started their preparations in class 9 onwards. All right. So there is already very high amount of pressure, all right, on students regarding their preparation. So trust me, if even if you are preparing for 2 years, if you're dedicating 2 years, you want to be to have a single focus for the 2 years to do a good job. All right. If you have a single focus, then you can still manage a very good rank. You can easily manage a top 500 rank, or maybe even a top 100 ranks are a little rare, but yes, you can definitely manage that also. But if you pick PCMB, then you are taking up one extra subject, one extra competition, so the pressure on you would be way higher. All right, so trust me, that will never be good because you will not be able to focus on one place full heartedly, and then you might get frustrated and you may feel the pressure. So my advice is just stick to one exam, go for PCM, take your JEE exam only. Okay, don't worry about it. Don't take too much pressure. All right, now as I was saying, there is one more thing that we can reduce. So we have all the equations with which, okay, what is electrical susceptibility? Okay, electric susceptibility, by the way, as I said, is a measure of how easily a dielectric or any material for that matter can get polarized. All right. Now, please note that electric susceptibility is always positive. There is no negative polarization because whenever you are getting polarized, every time the net polarization happens in the direction of external field only. It cannot happen opposite to that. That is why Xc is always positive. Okay, what you can do, Yasir, you can fill out a form in the description box below. All right, there you can give your details. You can request that you want to get in touch with me. All right, I will try and help you as much as I can. So please note that Xc is always greater than equal to 0, because of which your dielectric constant is always greater than equal to 1. All right. The Xc electric susceptibility would be 0 for vacuum because vacuum, cannot get polarized. For conductors, you can consider the electric susceptibility to be infinite. Why? The field inside a conductor would become 0. So you can say that its permittivity is infinite. So Xc is infinite. So please remember this. For any other medium, you can find Xc again experimentally. Xc will depend on the nature of the medium. Alright, so electric susceptibility is on the nature of the medium. So for water, it will be something else. For H2, it will be something else. For O2, it will be something else. So electric susceptibility is depending on the nature of the medium and hence is the dielectric constant. Alright, now you have all the equations like this. So you can use these equations. There is one more equation that you can derive, okay, which is about the bound charges that are appearing on the boundary of the dielectric. So I told you this relation, that here if there are negative charges appearing and if there are positive charges appearing here, all right, and if the density of bound charges is sigma b, then I told you that sigma b can be related to polarization vector as the magnitude of polarization vector. So let's just separate, isolate a region here. So you know that P equals sigma B. Alright. And you also know that P can be written as E net over or into epsilon naught into XC. Alright. Just let me rewrite that. So from here what I can say is that sigma B is equal to epsilon naught XC. And again, I can write E net as E external over 1 plus XC. Alright. Now please remember, if this external electric field, was being caused by, let's say, two metal plates. Alright, so this is the condition that you will see mostly. You will have capacitor plates, and in the middle of capacitor plates, you will have a dielectric. Alright, yesterday thermodynamic class was just awesome. Okay, thank you, but you were missing Jay Akash. I was wondering where you are. So this must have a positive charge here. So imagine that this dielectric was kept between two parallel plates, and this had a negative charge here. Alright. So your external fields would have looked like this. This would be E external. Alright. And your dielectric would have gotten polarized as shown. Okay, Yasir. So don't worry about it now. Now the Unacademy team will get in touch with me. They will give me your details and I will get in touch with you. Okay. Now, if the charge density on these plates is sigma, now that is referred as sigma free, because the charge density appearing on these would be of free charges. Right? You know, these are conducting plates. So on conducting plates, the charge that appears is called free charge. So if the charge density on these conductor plates is sigma free, Saren, how much time will I get connected to you? I think maybe maximum 2 days. Maximum 2 days. I think by tomorrow, this team you will share your number, and tomorrow or maximum by day after tomorrow, I will get in touch with you. Okay. So now I can also say that if this is the case, if the external electric field is being produced by conducting plates, so if Ex is produced by conducting plates, then I can say that E external is equal to sigma free over epsilon naught. Alright, so if I substitute that value here, then what I get is, if I substitute this here, then I get that sigma bound becomes equal to Xc over 1 plus Xc times sigma free. Alright, so remember this is also an important relation. Alright, or sometimes we also write this as, okay, sigma bound on this side. Sigma bound. So sometimes we also like to write it as, this can also be written as, in terms of dielectric constant, it is written as sigma bound equals K minus 1 over K. times sigma free. Alright. So you will be using this relation, by the way, so you need to remember this. So this is another important relation that you use in your capacitors when you're trying to relate the induced charge on the dielectric with the charges appearing on your capacitor plates. Okay, so Jay says, sir, I was not able to attend live, but I saw a recorded lecture because yesterday I was preparing for chemistry. Okay, no worries, no worries. So I tried to take everything from the basics. Okay, I hope you liked it, which you did, I guess. So it is fine. Yes, Yasir. So you're also a Navodian. Okay, all right. So you stay in a hostel then? Do you stay in a hostel? So please remember that these equations are very, very important. One, this equation is important. All right. And this equation is important. So on this page, I think these two equations are what you need to remember. Okay. So I hope everybody is sorted with the maths of polarization. Okay, so this is something very, very new which you haven't studied before. This is something that is not discussed a lot in most of the books. So you will need to take this slow, go through the video maybe a couple of times at least, try to understand what is happening. I've tried my best to explain this. Okay, and remember this. Okay, this was the equation. Okay, Akash. All right. By the way, this is the equation. This equation. This equation is written wrong in NCRT. Okay, so this equation is written wrong in NCRT. In NCRT, they have missed out on that epsilon naught. They have written this as P vector equals epsilon 0 into E net. No problem. All right. All right, Yasir. Don't worry. I will get connected with you in a couple of days. All right. So, but this is the correct equation. All right. I have verified this from a curriculum book of IIT. Okay. So when I was in IIT, I did this course. So the curriculum book that was used there gives the correct expression, which is this. In any case, where the NCRT people got wrong is that if you do not have this epsilon naught here, then Xc has dimensions, while Xc, electric susceptibility, is supposed to be a dimensionless number. Okay. Okay. I studied from a lot of books, and this is the simplified version of things. Okay, no book will show this like the way I have shown. I studied a lot of books, and this is the simplified version of what those books tell you. Okay. I know. Most of you guys haven't seen this. 1, 2, 3, 4. Actually, both Murli sir and me, we are conducting our own series. So we both will be covering all the topics. Okay. See, for 11th, I have already covered vectors. He has started vectors now. So similarly, that is the point. Both of us are supposed to cover all the topics. Okay. So I hope you get that 1, 2, 3, 4. It's not like I am supposed to cover a few topics and Murli sir is supposed to cover a few topics. Both of us are supposed to cover all the topics. Finally, you can study from whoever you are feeling comfortable with. Okay, but for JEE, we should follow NCRT method or else no. One JEE Mains would not ask you questions about this. This will be only asked in advance, and no matter what, this is the correct equation. So you always use this. Nobody can refute this because this is the correct equation. You find any book of international repute, they have this equation. All right. I have referred to a lot of international books. This equation is given in all the good international books, including one book that was a part of the curriculum in IIT Delhi. All right. Okay, so Jay Akash, sir, but for Jay, okay. So Shorts guy says, when is kinematics starting? Shorts guy, I have already finished kinematics for class 11th, by the way. I've already finished kinematics for class 11th. I just started Newton's laws yesterday for class 11th. So if you want, you can also go through my playlist of kinematics. I think there should be a playlist of kinematics for 2022. I have two playlists for kinematics, by the way, one for 2020 and one for 2022. The one meant for you would be that of 2022 because there I have discussed all the basics. Okay. Yes, shorts guy, all the teachers that Unacademy is taking are supposed to be good. Now, still, even if two teachers are good, they both have different styles of explanations, different styles of teaching, and you might feel more comfortable with one. Okay, so that is why you're just being given two options. Both of them are good. All right. If one was not good, then why would Unacademy even bring that person here? What's the point? Unacademy both brought two people because both were good, but both have very different styles of teaching. So now it is up to you which, whose style of teaching are you more comfortable with. Okay. All right. Now let's get back to capacitors, the topic that we were discussing. The entire discussion that we had about dielectrics was because we wanted to study what will happen if I insert a dielectric in the space between the capacitors. All right. Now, capacitance of any capacitor when filled with dielectric will increase. Now, why is that happening? You will realize that I discussed that what dielectrics do is that they reduce the magnitude of this E because they are producing their own E which is opposite, right? So if this was sigma here, you will have sigma induced here. This sigma induced would be creating its own field, which would be like this. So that results in a reduced field. Now, what does reduced field do? Reduced field is reducing the potential difference here. So you realize potential difference is going down, Q remains unchanged for the same Q. For the same Q, why? Because sigma is same. So if here sigma is same, the external E is same, but the net E is getting reduced because you put a dielectric in middle. So you realize that Q over delta V would go up. So when you insert a dielectric inside a capacitor, its capacitance increases. Okay, so Shorts guy says, for me, NLM, work power energy, vectors, COM just started rotational mechanics. Have a backlog of kinematics. Okay, so what you can do is, if you're looking for a quick revision, then you can follow my 2020 series. If you want a detailed study, then you can follow my 2022 series. Okay, Shorts guy. So that is why we are using dielectrics. The dielectrics increase the capacitance of capacitors. Okay, and the formula is again this. This is very straightforward. Again, this is very straightforward. You will realize that the electric field gets reduced by a factor of k. If electric field is getting reduced by a factor of k, potential difference is E times d. So potential difference is also getting reduced by a factor of k. So when you are calculating Q over delta V, the C is getting increased by a factor of k. All right. Now again, depends how detailed discussion you want. How detailed a discussion do you want? Like in my 2022 series, I have one entire slide which talks about displacement, one entire slide that talks about distance, then one entire slide which talks about relations between comparisons of distance and displacement. On the other hand, in 2020 series, I have just a single slide where I have discussed both distance and displacement. So you realize one was a quicker revision, one is a detailed explanation. So you should realize what you need more. All right. It's up to you what you think you need more. Okay. All right. Now, because of this, you realize whenever a dielectric is inserted, the capacitance is increasing by k times. Why? Because the electric field was reducing by k times. Similarly, the magnitude of induced charges, you realize this is the same equation that we discussed earlier. This is the same equation that we discussed earlier. This was the relation between the bound charges and the free charges. So here, this is the exact relationship that I have talked about later. Here you realize the two sigmas are related like this. If I multiply the areas of cross sections also, the two q's will also be related like this. So this is the equation that I am giving you. This is the equation between q, which is the charge on these plates, and q induced, which is the charge that is getting induced in the dielectric. All right. Now, what happens to the capacitance of a capacitor if it is partially filled with dielectric? So let us take a general case. So this is also a very specific case. All right. So first of all, let's stick to this. Okay. So first of all, let's imagine that there is a capacitor and it has a dielectric that has been placed somewhere. I don't know where. So let us assume it has been placed at a distance of x from one end. Then you realize that this distance would be d minus x minus t. Alright, this entire thickness was d, this was x, this was t, so this becomes d minus x minus t. Now let's imagine that this guy had positive charges. Alright, let's imagine this plate had positive charges. This plate had negative charges. So what would be the field? The field here would have been some E naught and inside would have been E naught over K. Alright, K is also called the relative permittivity, by the way. Alright, K is also called the relative permittivity. Why? If you remember, K was 1 plus XE. Alright, and 1 plus XE was, if you remember, that I said epsilon equals 1 plus XC times epsilon naught. Alright, so K can also be written as E over E epsilon 0, which is called the relative permittivity. Alright. Sir, I was hearing some controversies with Unacademy and it's trending on Twitter a few days ago. So I don't know, Shorts guy. I'm not aware what kind of controversy you're talking about. Okay, so I am really, as I said, I'm new to Unacademy. I joined them last month only, so I don't have much idea about what is going on. I did not even know there was a controversy. Okay, I'll probably also check out Twitter and see what is happening. Alright, so in any case, so how do I calculate the electric field? How do I calculate the formula for capacitance? It's very simple. You remember our approach of calculating capacitance? It was finding delta V and then finding Q over V. So first we need to do is to find what delta V is. So I will break my delta V into three parts. If the total potential difference from here to here, is delta V, now I am going to break this into three parts. Between here and here, I will call delta V1. Between here and here, I will call this delta V2. And between here and here, I can call this delta V3. Alright, now it is very easy for me to see. Delta V1, which is the potential difference in the first region, would be E naught times X. Similarly, delta V2 would be E naught over K times T. Alright, because there the electric field is getting reduced by a factor of K. Okay. Similarly, delta V3 is E naught over D minus X minus T. Alright, hi Arnav, how are you? Okay, so it's something related to teachers where the Unacademy team are telling teachers to take classes and not paying them. Many teachers are furious, making videos on YT. Okay, I don't know much about this. I'll find out if that is true or not. I have no idea because in my experience, I mean, I have gotten paid, so I don't know what is happening here. So delta would be summation of all the delta VIs. So all I need to do is add all these up. When I add all these up, I can take E naught common. And in the bracket, I will have X plus T over K plus 1 over, okay, I've oh, here it would be multiplied. Yeah, that's what I was wondering. Here it would be multiplied. Alright, so this would be d minus x minus t. Alright, so you realize this x gets cancelled and I'm getting my E naught times t over k plus d minus t. Alright, now E naught was sigma over epsilon 0. Okay, so please remember this. So now I can also rewrite this as delta V equals sigma over epsilon 0 times t over k minus plus d minus t. Alright, now sigma again becomes q over a. So this is q over a epsilon 0 t over k plus d minus t. Alright, now from here I can finally find the capacitance. The capacitance C would be nothing but q over delta V, which will become epsilon naught A over T by K plus D minus T. Oh. So this is the relation that I have for capacitance of a capacitor which is partially filled with a dielectric. So please remember this. This you will need to memorize. Okay, I was surprised that even in the field of education controversies are going on. Yes, it happens everywhere. Shorts guy. Sir, what do you do as a job? This is my full-time job, Arnav. This is my full-time job, teaching physics. I've been teaching physics for JEE for the past 8 years. Alright. Next, if there were multiple dielectrics, so let's get rid of this. Okay, so let's I don't know. Instead make another diagram wherein you have multiple dielectrics. Okay, so let's say you have a dielectric like this, and you have a dielectric like this, and so on. Maybe let's draw one more. Alright. So all these dielectrics, let's see, this has a thickness T1, this has a thickness T2, this has a thickness T3, and this has dielectric constant K1, dielectric constant K2, and dielectric constant K3. And this entire length is D. Then, following a similar logic, following a similar derivation that I showed you here, you will find that I'm directly writing the result. You can check it in any of the textbooks also. You will find that C would be equal to epsilon naught A over T1 over K1 plus T2 over K2, so on. And finally, D minus summation of all T over 1. So this is what I can write my capacitance as. So even if you have multiple plates, this is how you can find the capacitance. Now, if there was a metal plate in the middle, then you can take K of that as infinity. So please remember, you can use this formula. This formula is wonderful. This will work for every situation. You realize what I'm doing is that all the space that was left, all the space that was not filled with the dielectrics, so it was filled with air. Now I can consider air also another dielectric which has dielectric constant 1. So what I need to do is every gap, its thickness over its dielectric constant, thickness over dielectric constant. That is what you are doing. So please remember this, that this is the formula. The numerator you have epsilon naught A, and in denominator you have thickness over dielectric constant plus thickness 2 over dielectric constant 2 plus thickness 3 over dielectric constant 3 and so on. Alright, so chinna chinna, when the laws of motion class, that will be tomorrow chinna chinna. Alright, so that is it. That is where I would like to end the discussion for the day. You can take screenshots of these problems and practice them on your own. Alright, so this will be your homework problem. Alright, so please take a screenshot of this and try this after the class as a homework assignment. Alright, so let me read out the question. This question says a capacitor has two circular plates whose radius are 8 centimeter and the distance between them is 1 mm. Time 4 o'clock. 4 o'clock chinna chinna. Okay, 4 o'clock in the evening. So when mica plate is placed between the two plates, you have to calculate the capacitance of a capacitor and the energy stored when it is given a potential of 150. Alright, so even when you're trying to calculate the energy stored, instead of half CV square, now you put the new C. Okay. Next, another problem for your homework. Alright, so this also you should be trying after this class. Okay, so take a screenshot of this. Try this once you are done watching the lecture. Hi Yolo, how are you? So here the question says a capacitor stores 50 microcoulomb charge when connected across a battery. When the gap between the plates is filled with the dielectric, the charge of 100 microcoulomb flows through the battery. Okay, what is the dielectric constant of the material inserted? So you guys try this problem and I will discuss this in the next lecture. This is a very interesting topic which is asked a lot. So I would want to discuss this in the next topic after you have already tried this once. Okay, so that is it guys. There is one last thing related to dielectrics which is called dielectric breakdown. Alright, so let's go over this quickly and I'll finish the lecture for today then. So when the electric field across a dielectric is increased beyond a point. So as I said, when you are keeping a dielectric in electric field, what is happening? It was getting polarized. Alright, so my dielectric was getting polarized because all the electron clouds were getting distorted. All the electrons are being pulled by the electric fields. Alright. Now what happens if I keep on increasing my external electric field? So here you have minus plus, all the dipoles are appearing like this because of the external electric field. So minus plus. Alright, that is what is happening. Now, if I keep on increasing the strength of the electric field that I'm applying, you see, higher the electric field, higher is the pull that they exert on all these electrons. So all these electrons were getting distorted, but they were still revolving around the nuclei. They were still tied to nuclei. Alright. Now what happens is that if I keep on increasing the strength, there will come a point when the electric fields would be able to pull the electrons out of their orbits. Alright, out of their molecules. And then they will become free electrons like you have in conductors. And that is when you will see current flowing through a dielectric. Alright. So please remember this. If you keep on increasing the electric field across a dielectric, then beyond a point, the force of this electric field will start pulling the electrons out of their orbits. Now, these electrons will become free electrons and they will start conduction of electricity now. Now, due to high resistance, like I told you, dielectrics are nothing but insulators. Insulators have very high resistance. So due to the high resistance of insulators, what happens is when current starts flowing through them, it produces a lot of heat. So you see that it gets burned also. The material gets destroyed and that is called a dielectric breakdown. So I don't know if you have noticed, in the old days they used to have this tube light, right? And they used to have some circular thing which is attached to it, and sometimes that would fuse, it would go black. Okay, so that's a small condenser, or condenser is another term which we use for capacitors. So that was the dielectric breakdown of condenser. When it goes black, inside the dielectric gets charred, it gets burned. In fact, your lightning is also an example of dielectric breakdown of air. So when clouds are approaching each other, they are creating electric field lines between them. And if there is strong enough electric field line, You know, air is a bad conductor of electricity. Air is a dielectric. But if the electric field strength between the clouds becomes high enough, then the current starts flowing through air. Alright, and that is what your lightning is. And that is why lightning comes with so much of heat and light. Why? Because of the high resistance of air. So that is also an example of dielectric breakdown. So you will always want to keep the strength of the electric field in a capacitor below the dielectric strength or breakdown strength of the dielectric. Alright, so please remember this. So that is it where I wanted to wrap up today's lecture. We will discuss some more problems in the next class. So this is where I will take your leave. Now before I leave you, let me remind you that you can get your Unacademy subscriptions by installing the app, then going to the plus section, selecting your goal as IIT JEE and clicking on that get subscription button. Now also remember that you can use my code RDLive to get your Unacademy subscriptions if you want to enroll in my courses, if you want to study from me. So this code will not only unlock all the awesome features of Unacademy Plus for you, it will also give you an additional 10% off. Now if you like today's video, then please press the like button and share it with your friends as much as possible. The PDF notes of all the slides used in today's lecture would be available for download by day after tomorrow. Alright, if you're following us on the JEE English channel, then you can connect with us on the Telegram app using the link shown above. Now before I leave you, please remember that you can join the Unacademy, you can get the Unacademy subscription using this code. This is my code RDLive. Use this code while getting your Unacademy subscription and get another additional 10% off. Alright, that's it from my side. So take care, keep studying, keep practicing, and I'll see you day after tomorrow.